Thank you. Thank you very much. I'd like to thank everyone for warm hospitality this week and the warm weather. Earlier I had texted my wife and told her I was sitting by the pool, and it was quite sunny and warm. And back in Cincinnati, Ohio, it's 7 degrees Celsius, so she said I was mean. So I'm going to talk... let me do this. First, I'd like to say, NIOSH, we welcome every opportunity we have to present the work that we've done, the research that we're involved with, and how that applies to safety and health for folks that need that information. So we appreciate the opportunity to do this. What I'm going to focus on today is a discussion about a little bit about the Health Hazard Evaluation Program, which is what I'm part of. And then I'm going to focus on what we've learned in our experience with evaluating noise in the workplace and noise control. So NIOSH was established back in 1970 as part of the U.S. Occupational Safety and Health Act of 1970. During that act, the Occupational Safety Health Administration was formed, as well as NIOSH. So OSHA was established to not only establish safety and health law, but also to enforce safety and health law. NIOSH was established for occupational safety and health research, and then also to disseminate that information to stakeholders, to folks that might need that information. So this is a list of the many things that we are involved with, primarily occupational safety and health research, surveillance epidemiology work, the Health Hazard Evaluation Program, which is what I'm part of, and Dr. Grimes, who spoke yesterday, is also part of the Health Hazard Evaluation Program. We're involved with different types of field studies, laboratory studies, personal protective equipment, respirator testing and certification, safety research. A lot of what we do is, as a result of our research, we are developing and distributing educational safety and health materials for stakeholders, for folks that are interested and can use that information. Nowadays, all of that information is published on the NIOSH website. So all of that is available. And then last, I want to mention that we are involved with protecting emergency response workers. So the pictures that we have on the slide reflect some of the work that we've done. The top picture we have is a couple of colleagues of mine that went out onto an oil platform after the Gulf oil spill several years ago. They were monitoring for chemicals in the air on that oil platform. And then the picture on the bottom was after the terrorist attacks in 2001, where we were on the ground trying to assess the first responders, their work, their exposures, and try to protect them from hazards that they may encounter. Okay, very briefly, the Health Hazard Evaluation Program. What we do is we respond to requests about a safety and health concern or an occupational health concern in the workplace. So we get requests from employers, employees, unions, and also other government agencies in the U.S. As part of that request, we're going to respond to what their concerns are. So it could be chemical hazards, could be physical hazards such as noise or ergonomics, radiation, biological hazards, and psychosocial workplace stressors. Throughout the whole process of doing a health hazard evaluation, we involve both the employers and the employees in that process. So when we're doing a walkthrough of the facility or we're having meetings with folks in a facility, employers and employees are represented and are participating in that process. At the end of our process, what we do is we issue a final report that has our findings. So not only what we've seen and observed, but we'll provide recommendations on what folks need to do, what people need to do to correct those hazards that we've seen. And very importantly, for a lot of companies, there's no cost for what we do. We're funded through the Centers for Disease Control and the U.S. Department of Health and Human Services. So there isn't a cost for our work activities. So when we're talking about noise exposure and hearing loss, just very briefly, I want to just mention the mechanism for hearing loss. So what's happening in the inner ear is when a person is exposed to noise, it deflects the hair cells in the inner ear. The hair cells, the movement of the hair cells sends nerve impulses to the brain, which we interpret as sound or as noise. So when we have repeated exposures to high levels of sound, those hair cells will eventually get damaged. So they might separate from the tectoral membrane within the inner ear, within the cochlea. Once those hair cells are damaged, there isn't a mechanism to restore those in humans. So I'm going to first talk a little bit about noise evaluations and how we do some of our noise evaluations. But before I get to that, I want to mention just the different types of sound that occur in the workplace. So in some workplaces, we might have exposure to continuous noise. This is sound that pretty much is the same throughout the day. So the picture on your left is a rotary printer, and this is a company that makes aluminum cans, and this is printing the label on the aluminum can. So a soda can or a beer can. This machine operates pretty much continuously throughout the workday. So workers that are at this process, monitoring this process, they have pretty much the same exposure for the entire duration of the work shift. At times, we have folks with intermittent exposures. So the worker at the table saw on your right, when they were running the table saw, they have a high level of noise exposure. Their exposure is going to be 95 to 100 decibels in most cases. But then they also have periods where their exposure is lower, where maybe they're doing some assembly work, but they're not running the table saw. So during those periods, their exposure might be somewhat less. We can have exposure in the workplace, exposure to impulsive noise. And I've defined it there in the bottom. So when we're talking about impulsive noise, it's like a hammer hitting an object. It's a steep rise in sound followed by a rapid decay with 1 second separating those. So a good example are someone shooting a firearm. So the picture on your right is a law enforcement training center where folks these are Department of Energy employees in the U.S. They're training for responding if they need to respond. So they do training exercises, and as a result of those training exercises, they're firing blanks in these actual firearms in this circumstance, but they have impulsive noise exposure, as you would expect from gunfire. And just to highlight, NIOSH has done quite a bit of research in this area. One of my colleagues, Bill Murphy, has done a lot of research in this area looking at the sound levels from weapons fire, from firearms. And so generally, we're getting exposures from 155 to 170 decibels when someone is firing a weapon or a firearm. The picture on your left, that's a hammer forge. So that is an operation where someone is taking a molten piece of metal. It's a piece of metal heated to about 2,400 degrees Fahrenheit, and they're hammering that into shape with mechanical action, with a pneumatic hammer. And that generates sound levels up to 150 plus decibels at times when that hammer is striking the forge piece. In workplaces, we also find a combination of noise where we have both continuous and impulsive noise. This is a workplace that I had monitored many years ago. They're actually constructing. This is the back of a trailer that you might see on the highway that's used to haul new cars from the factory to the showroom. So they're doing some repair work on this trailer. So an activity like welding typically involves you get noise from the welding process, and then in addition to that, you get noise from grinding. Usually those things are done at the same time. But then they also are occasionally doing hammering, so they may have impulsive noise from the hammering. So it's really a work environment where you have a lot of different types of noise that are occurring. And all of these things are important because how we monitor that or how we interpret the noise exposure might depend on the type of noise that workers are exposed to. So just a rule of thumb, if we don't have an instrument to take a measurement, if I'm about 1 meter away from another person in a workplace and I have to raise my voice for that other person to be able to hear me, probably the noise level is too loud. I'm probably close to a level that might require the use of hearing protection. This is just an example of different types of noise levels and what those noise levels are. And I'll get into what the level that we consider hazardous. That's right around 85 decibels. But if we look at this chart, typically when we're having a conversation, we're conversing around 50 to 60 decibels. That's how loud it is when people are conversing. If we're at a busy restaurant, might be 80 to 90 decibels if there's a lot of noise in the restaurant. In someone using power tools, like a saw of some sort, a power saw, that's going to be in the range of 90 to 100 decibels. And then all the way up to an airplane taking off on the runway, we're going to be approaching 140 decibels. If you're on an aircraft carrier, military aircraft, when they take off, that's about 170 decibels. So that's even greater than what we're seeing in a municipal airport. So I do want to highlight the noise exposure limit. I briefly mentioned 85 decibels. So NIOSH considers when we have an 8-hour time-weighted average, so when a worker's average exposure over the duration of their work shift averages 85 decibels, that's considered our recommended exposure limit. When that is exceeded, NIOSH recommends that there are certain things that a company put into place. So when the REL is exceeded, what we recommend is that a company implements a hearing loss prevention program. Sometimes it's referred to as a hearing conservation program. So the things that we're going to recommend that a company do under those circumstances is to establish engineering controls, administrative controls, or work practice controls. All of these are efforts to reduce the noise exposure levels. So we want that to be the first thing that they try. Hearing conservation program or hearing loss prevention program might also involve providing hearing protection. And I'm going to talk a little bit about hearing protection a little bit later in my talk. Hearing protection also involves making sure it fits properly and people are trained how to use it properly. And then we also recommend providing baseline and annual audiometric testing. This is hearing testing to assess a worker's hearing level, how well their ears work, before they start working in that workplace, and then every year thereafter to ensure that they are not losing their hearing as part of their exposure to noise in the workplace. So I mentioned our REL is 85 decibels. So one of the ways you can think of it is for every increase of 3 decibels, we need to have the exposure time. So if I'm exposed to 88 decibels for 4 hours, that's the equivalent of being exposed to 85 decibels for 8 hours. If I'm exposed to 100 decibels in the workplace, once I have 15 minutes of exposure at 100 decibels, that's the exact same as being exposed to 85 decibels for 8 hours. One of the things NIOSH does, and one of the things that we've seen over the past probably 10 years that I've been doing working at NIOSH and doing industrial hygiene, past 10, 12 years or so, is that a lot more companies are using extended work shifts. So instead of workers working only 8 hours during the work shift, they're working 10 hours, 11, 12 hours. So one of the things that NIOSH does is we adjust the exposure limit for those longer work shifts. So NIOSH adjusts the exposure level to 84 decibels if it's a 10-hour work shift. We adjust to 83.2 decibels if it's a 12-hour work shift. Now we do have, so NIOSH are recommended exposure limits. I mentioned earlier that NIOSH doesn't establish safety and health regulation, nor do we enforce safety and health regulation. So in the United States, the Occupational Safety and Health Administration actually establishes the noise exposure limits that are legally enforceable. Their limits, OSHA's limits, are slightly different than NIOSH. They have a limit of 90 decibels as a permissible exposure limit. One of the things that we advocate is that companies should follow NIOSH guidelines because they're more protective of hearing and preventing hearing loss in the workplace. So looking at the instruments that we use to measure noise exposure, there are 2 instruments that we are primarily using for measuring noise exposure. In most of the circumstances when I go out into the workplace, I'm taking both of these instruments, noise dosimeter and a sound level meter. So I'll talk a little bit about both of these. So with our noise dosimeter, what I'm going to use that for is I'm going to do personal noise monitoring. So the worker is going to wear a noise dosimeter. They're going to have a small microphone that we're going to attach midway between their neck and their shoulder, and that's going to give us an estimation of what their noise exposure is for the duration of their work shift. So they're taking that with them wherever they go. I do want to mention, I'm not going to spend much time on this, but when a person has a noise dosimeter, setting up the noise dosimeter for taking exposure measurements, there are certain dosimeter settings that should be used. These are the settings that NIOSH recommends. A response rate of slow, A weighting. The weighting scales, really, A weighting is a scale that measures noise across the frequencies, but diminishes the effect of the lower frequency noise to mimic or match how people respond or how we interpret loudness of noise. So, for example, if I heard an 80 decibel noise at a frequency of 20 hertz, it's not going to sound nearly as loud as an 80 decibel noise at a frequency of 1,000 hertz. Even though the energy for both of those is the exact same, how I perceive the loudness is very different. I'm going to perceive the noise at 1,000 hertz to be substantially louder. So A weighting is just a way of dealing with that. I have a note here. Always make sure that the instruments are calibrated before and after the work shift, before and after you take measurements to ensure that the instrument is working as you expect it to work. So our sound level meter and octoband analyzer, that's going to be our instruments that we're going to use primarily for doing area noise monitoring. We're going to use that to maybe do an assessment of where noise exposures are likely to be high. I might use it to identify where are my sources of noise. I might use this to do task-based measurements, and I'll briefly talk a little bit about that coming up. The octoband analyzer portion of this instrument allows me to look at what are the noise levels at different frequencies. So that's going to help me determine what type of noise control might be the most appropriate for that work area or for that piece of equipment. I mentioned accuracy. There are different levels of accuracy. So there are instruments that are have greater accuracy. They're considered Type 1 instruments, and all that means, Type 1 means, is that they're required by law or by specification that they're going to have an accuracy of plus or minus 1 decibel at 1,000 hertz. A Type 2 instrument is a little bit less accurate. Now, what we see these days is that most instruments are much, much better than that. So the accuracy is very good in the modern instruments. So when I'm in the workplace trying to take noise exposures, how am I going to do that? What are my approaches? What are the approaches that we use in the workplace? So really the best method is what I've mentioned with the noise dosimeter, is to use a noise dosimeter. The worker wears that noise dosimeter with the microphone for the entire duration of their work shift, and that will give me a very good estimate of what their noise exposure is. It allows me to know, are they overexposed? If they are, how much are they over the exposure limit? But there are circumstances where a company or someone may not have a noise dosimeter. So what are the next best methods that we can use? Well, we can do task-based monitor, and we can do area noise monitoring. And those generally are going to be, that's generally going to be monitoring that we're going to be using a sound level meter for. So with task-based monitoring, a couple of things that I need to do to know that. And I did a pretty large study a number of years ago when I first came to NIOSH, where we were looking at different methods for task-based monitoring. But if I'm doing task-based monitoring, I need to know a couple different things. I need to know what are the different job tasks that the worker is doing. So yeah, this is an example of a worker that's doing a repair, is in a repair type job at an automobile manufacturer. So this worker has a couple of different tasks that they're doing throughout the day. Yeah, they, of course, have their break time where they have very little noise exposure. They spend some time in the welding department doing repairs. They spend some time in the press department doing repairs. And they spend the time in the tool and die area. So once I know what their different job tasks are, the next thing I need to know is how much time do they spend in each of those tasks. So we're looking at, in the welding department, in this example, the worker is spending about 2 hours in the welding department every day. And then the third piece of information I really need to know is what is the sound level during each of those tasks. So if I'm doing task-based monitoring, I'm going to find out what are the work tasks that the worker has, how much time do they spend at each task, and identifying the time at task might be multifactorial. I might ask the worker, how much time do you spend in the welding department every day? I might ask the managers, how much time do your workers spend in the welding department every day? Well, we're going to try to get a good idea of how much time they spend at each task. And then I'm going to take sound level measurements using a sound level meter during each of those tasks. I may take several measurements during each of those tasks and identify what is the noise level in the task. So in this example, in the welding department, the sound level is 88.5 decibels. So putting all of that together, we can actually calculate and get an estimate of what their time-weighted average exposure might be. I'm not going to ask you to memorize the formula, but it's a formula to identify this is what the average exposure is going to be based on all of that input of information. So it can be if all of this information is good quality information, the estimate at the end of this calculation is usually a fairly good estimate, is what we found in some of our previous research. So we're going to use a sound level meter for doing area noise monitoring. That's a younger version of myself, and this is actually a veterinary clinic, and this is the area where they keep the dogs before they're having surgery or before the veterinarian is going to see them. You can't really see it in this picture, but there's a dog right there. So generally, people aren't working in this area. They go back into this area to get the dogs, do some care for the dogs, feed the dogs, that type of thing. But when anyone goes back into this particular area in a veterinary clinic, and this is going to be in any veterinary clinic, the dogs start barking. One dog barks, and then the rest of the dogs bark. So it's about 100 decibels or more in these areas. So we were taking measurements in this area. And so one of the things that we recommended were when people go into these work areas, they should be wearing hearing protection. Now, one of my colleagues did several studies in veterinary practices looking at noise exposure in the kennel areas where dogs might be kept overnight and looking at noise exposures. And he actually was looking at potential noise controls for those areas. But the noise levels are substantially loud when dogs are barking. So one of the things that is important to consider when we're doing area noise monitoring is how many measurements we actually take. So this is a time history of a worker's noise exposure, and this is pretty typical of noise exposures in workplaces, where at some points in the day we may have high levels of exposure, at other points we may have low levels of exposure. So what if we only took one measurement, one noise measurement? I happen to take the measurement right around 10 o'clock in the morning. If I took a measurement at 10 o'clock, it may look like, okay, the exposure is 77 decibels. That's not too bad. But what if I took a measurement later on in the day, around 12:30, 1 o'clock? The level might be 100 decibels at that point in time. So I might be thinking, okay, it's pretty darn loud. So to get a really good picture of what noise exposures are and have a sense of what is that worker exposed to, what we recommend is taking several measurements throughout the day. This will give us a good idea of what are the worker's exposures as the work shift proceeds. And we're looking at, and these periods of high and low level exposure may represent different work tasks. So that's one of the things that we do when we're in a workplace is we spend a lot of time observing what are workers doing, how are they doing it, what equipment are they using, and that gives us an idea of not only what noise levels might be generated, but also gives us an idea of what type of noise controls might be most appropriate when we're talking about trying to reduce noise exposures. Some workplaces do area noise mapping, and this is just taking noise measurements in different areas. I don't do a lot of this just because we have dosimeters and we can actually take dosimetry measurements on all the workers. But this is often a pretty effective way of at least getting a rough idea on what noise levels are throughout the workplace. So in this example, what I'm seeing is the noise levels in the storage and shipping area fairly low. Remember, the level that I'm concerned about is around 85 decibels. So that's my reference point. So I'm looking for areas that we have noise levels either at or near or above 85 decibels. So the way I would use this information, or the way people typically use this information, is it may be an indicator of it may be an indicator of where do we need to do additional noise monitoring of workers to find out exactly, are most of these workers actually exposed to noise levels above 85, above our recommended exposure limit, or are they under that? This area is pretty loud. We might want to do some assessment for noise controls. So we're using that information kind of to guide us on the next steps. And it also gives an indication if somebody's walking through the workplace, what are the noise levels as they're going through different work areas. A lot of times companies will have visitors going through the workplace, and so they may require visitors if they're walking into these areas right here to wear hearing protection while they're in those areas. If the visitors only needed to go to the shipping and receiving department, then maybe they don't need hearing protection. So going through just some additional considerations on when we're talking about doing noise assessments and noise evaluations in the workplace. I mentioned this first bullet already. I think it's critically important as an industrial hygienist, as a safety and health professional, to spend a lot of time observing what's going on in the workplace. And so I'll just re-emphasize that. Find out what workers are doing, how they're doing it, what equipment they're using, and how that interacts with their noise control, or how that might be affecting their noise control. Sometimes we have a number of different workers doing the same job. So I might have 50 workers doing the exact same job. So one of the questions that comes up in the industrial hygiene community is how many samples do I need to collect from that group of workers? So for a group of workers where we're all doing the same thing, we might group those workers into what we refer to as a similar exposure group. And the rule of thumb for that is I'm going to try to do measurements. If I'm doing dosimetry, I'm going to try to do measurements on about 10 to 25% of those workers, if I have the resources to do that. An important thing to consider, and these are questions that we ask before we go into a workplace for health hazard evaluations, or when we're walking through a workplace and getting some background information, when and where we need to sample. Are there differences between the first, second, and third shift in what workers are doing? So in many cases we find that higher noise exposures, or the most work activity, is occurring on the first work shift, the day shift, if you will. And so maybe that's the shift we want to do our noise monitoring. But we may find that there's different work activities, different processes occurring on the second and third shift that might be different than the first shift, or might be different than the other two work shifts. So in those circumstances, we might want to make sure we're doing some monitoring on not only during the day shift, but also during those other work shifts. Sometimes we find that there are different noise levels in the morning versus the evening. Maybe workers are doing something slightly different in the afternoon versus the morning. We see this not infrequently. What we find sometimes when we go to a workplace after, sometimes people have had previous monitoring done by a consultant where perhaps they didn't do a full shift of monitoring, and so they may have missed some exposures that employees have, and so they're missing some important information. Are there differences between tasks? Yeah, that was reflected earlier in the slide I had previously where we're looking at different work tasks that employees are doing, where we saw a welding task had lower exposures than a press operation task or the press area. And differences in equipment or processes. Sometimes we might find that a workplace has several of the same types of machinery, but we may find that one or two pieces of those machinery or pieces of equipment have higher noise levels than other ones. And that might be a reflection on maybe one piece of equipment is older, maybe one piece of equipment has it has a maintenance issue, needs to be repaired. And we're always, when we go into the workplace, I mean, we're always looking for, are there ways to reduce noise levels in the workplace? I mean, my goal when I go into a workplace is I would like to see everybody under 85 decibels for their exposure. So when I'm going into a workplace and looking at what are the noise levels, what are the characteristics of noise, I'm also thinking about what types of things might we be able to do to reduce those noise levels in that workplace. So I'm going to move on. I'm going to move on to talking a little bit about noise control. So our last bullet. This is an example of a sound level meter, an octoband analyzer I'm using in a foundry. And I've got a number of pictures from a foundry. Foundries generate quite a bit of noise, so you're going to have a lot of loud noises, a lot of noise exposure, a lot of risk of hearing loss. You may have seen this slide before or something similar to that. When we are talking about controlling hazards in the workplace, whether it be air contaminant hazards, biological hazards, any type of hazard, we always go back and focus on the concept of hierarchy of controls. So if there's a way, if we're talking about noise, if there's a way to eliminate that source of noise, we might do that. That's something that we want to encourage. If there's a way of substituting a loud piece of equipment, loud piece of machinery with a piece of machinery that is quieter, yeah, that might be a focus that we might do. I mentioned the hammer forge earlier. So a number of years ago, I visited a company that had hammer forges. High noise exposures, excessively high. This company actually had a sister company that instead of using a mechanical action to forge a molten piece of metal, they actually had hydraulic forges that would gently squeeze that piece of metal into a shape. Now that can't be used for all parts, but a hydraulic forge generates much less noise exposure than a hammer forge. And our engineering controls are going to be our way of reducing noise level at the source, at the piece of equipment, and I'm going to get into some of those techniques, some of the things that we might do. Administrative controls, I've got a slide or two that demonstrate things that I might do to change the way people work that might generate less noise. We're working with a company right now. We haven't done a site visit yet, but they are using doing some sawing on metal. They have noise exposures over 110 decibels. So one of the things that they're doing as an interim are they're only allowing employees to work 4 hours during their work shift at that high noise area, and then the rest of the other 4 hours of the work shift they're working in a lower noise area. And that's just a mechanism to try to reduce their overall noise exposure. And last but not least, personal protective equipment. But we always want to focus on doing these other things before we get to personal protective equipment. So I mentioned measuring noise frequencies. So my octoband analyzer of my sound level meter is going to measure noise frequency levels. And so it's going to let me know what is the noise level at each of these frequencies, from low frequencies to high frequencies. And what does that tell us about noise control and what we want to do? So if I take noise frequency measurements and I find that my highest noise levels are in these high frequencies, so that's going to tell me that it's high frequency noise, it's highly directional, very reflected, and I'm going to use these types of noise controls. I'm going to look at using enclosures, noise barriers. I'm going to look at compressed air noise is generally high frequency. I'm going to look at controlling compressed air noise. If I do octoband measurements and I find that this is what's occurring, in this circumstance we have very high noise levels at 31.5 hertz, very high noise levels right around 315 hertz. So this is low frequency noise. What this tells me is it's probably vibrational in nature. It's from a piece of equipment that's generating vibration. And so my approach to noise control is going to be very different than in the previous example. I'm going to be looking at trying to isolate that vibration. And I will give examples of that for all of you. Okay, this is just an example of an enclosure that we might use for reducing high-frequency noise. So here's a worker working at a riveting machine. So most of the worker's noise exposure is coming from right in front of them. But because of the nature of this work, we might be able to install a partial enclosure in this circumstance. So what the noise control option here is an enclosure with a safety glass in the front so the worker can see what they're doing, but then you have absorptive material on the inside to reduce some of that reflected noise that you get from high frequency. And in this example, what we're seeing is the noise level before this control is put in place, the noise level right here. We're having a lot of high frequency noise, right around 95 decibels. After this noise control is put in place, that's reduced to below 85 decibels. So that might result in a substantial noise exposure reduction for that worker. Here's a situation. This was a drug manufacturer. So this is just a piece of equipment that's part of that process. So it's generating high-frequency noise. And I don't have the octave-band chart for you. But they've installed an enclosure around this machine. It was actually a pretty good enclosure. They put this in themselves. Their maintenance department or their maintenance folks built this enclosure. It's closing the machine. So it's a little difficult for you all to see, perhaps, but there's an opening right here in this enclosure. So they're getting leaking of this high-frequency noise in this work area. So if I recall correctly, these workers, their exposures were right around 88, 89 decibels. So remember, I want to get those exposures down to below 85. So one of the things that we suggested here was take things one step further. So let's make sure we're enclosing this gap, just making this gap a little bit smaller. And that may result in a little bit less noise exposure, might reduce some of the high-frequency noise in that area. So I'm excited, or I applaud companies when they've taken the initiative and they've installed some noise controls on their own. It's exciting for me to see. I'm kind of a noise geek, so it's exciting to see. This is a company I went to. This is a result of a control measure that they put in place. So this is a company that made galvanized pipe, galvanized conduit. So one of the things in this process was after they would galvanize it, they would pull a piece of pipe out of the galvanizing tank and then blow high-pressure steam through the pipe to clear out excess fluid from the inside of the pipe. So that steam, it created a lot of high frequency. It was just this hiss sound like that as the steam blew that excess fluid out of the pipe. What we found was that high pressure steam was generating about 135 decibels of noise as it was actually blowing the fluid out of the pipe. But workers in this area, their time-weighted average exposure was right around 95 to 97 decibels. So one of the things we suggested was, why don't we build an operator control booth? So the workers would stand near this process, and I'm sorry I don't have a picture of the actual process. The workers would stand near the process and observe it, and they had a control stand where they had some of the equipment controls. So using our suggestion, the company actually built a really nice control booth. They moved the equipment controls into this booth so the worker could spend part of the day in this booth. At times, they would go in and out of the booth, but they could spend part of their day inside this booth running the equipment, keeping track of making sure everything is operating as it's supposed to be operating. And what we found when we returned for a site visit was they had more than a 15 decibel noise reduction by installing this booth and using that booth. So a very nice control measure they had done. This company had done several other controls also to reduce some of the noise levels. So I'm going to briefly talk about direct and reflected sound and how we might want to control that. So this is just an example, a figure showing a worker at a noisy machine. So most of that worker's noise exposure is going to be coming directly from the machine they're working at. And they're probably going to have a pretty high level of exposure. But in this example, we've got a workplace that is, another part of the workplace is a relatively quiet operation. They're assembling, they're putting things in boxes, putting parts in boxes. but overall, that process itself doesn't generate noise. So most of these workers, their exposure is coming from here. So how do we want to control that noise? Well, they're getting, first of all, they're getting direct noise from the equipment, but because of the surfaces in this workplace, the hard ceiling, the walls, we're getting a reflection of noise reflecting off of the ceiling, off the walls, and affecting the noise levels in this quiet operation. And we've seen this in a number of places. So one of the strategies that a company could use in this circumstance is a combination of two things. One is a noise barrier. So we're having a separation of these workers in this quiet area from the noisy equipment. So separation. And then they're installing acoustic absorption material on the ceiling. That's going to reduce some of this reflected sound. So even though the sound is still traveling to the ceiling, it's going to reduce some of that reflection. And as a result, these workers' overall noise exposure. A couple of things about sound absorption treatment. This is a foundry again, different foundry. A couple things about absorptive treatment is I want to just reiterate or re-emphasize that absorptive treatment doesn't affect the workers who have direct noise exposures. So this is a worker, and I've got another picture of this a little bit later. This is a worker working at a 30-inch grinder. So they're grinding a metal part on this grinder. So most of their noise exposure is coming from the grinder itself. It's coming right at them. This company had installed absorptive material on the walls and ceiling with the hopes that it was going to reduce that worker's noise exposure. But it's not going to have much of an effect in this circumstance. I also want to highlight, this is from the same company, this is a different work area within the company. They have a perforated metal material to try to reduce some of the noise. And what we found with this metal material, this perforation, was these things were completely filled with dust. So maintenance of that type of noise control or that type of absorptive treatment requires a bit of maintenance, and they installed it in an area that was quite dusty. So once that thing fills with dust, the effectiveness of it is going to be substantially reduced. So I mentioned the sound barriers. They're not something that's going to work well for low-frequency noise. It's going to be something that we would be using for high-frequency noise, at reducing direct noise. When we're using barriers, like in the example a couple slides ago, we want to place it either as close to the source, to the employee, or as close to the source of noise as possible. And usually for a barrier, we're going to make it out of a dense material, but then we're going to line it on particularly the side facing the noise source with an absorptive material to reduce some of the reflected noise. Here's an example of this is another example in a foundry. And in this example, this is a cylinder. Metal parts would come out of the cylinder and then drop down onto this conveyor below it. The conveyor was a shaker conveyor, and it would move parts to another part of the process. So there was quite a bit of high-frequency noise generated by this cylinder as the parts were coming through. So the company had installed a barrier which employees could either move into or out of place. One of the things that we found was when the barrier was not in place, we have a lot of high-frequency noise, right around 100 decibels. When the barrier was in place, that high-frequency noise was reduced some. It was reduced about 10 decibels, 5 to 10 decibels, maybe more in some of the very higher frequencies. And this was just a matter of, well, let me also mention, so these workers had very high noise exposures, about 113 decibels in this work area without that barrier in place, 108 with the barrier in place. So either case, we've got a lot of noise exposure. But anything they can do to reduce that is moving things in the right direction. So putting this barrier in place was really just a matter of employees doing it. So there was nothing fancy about it, nothing automated about it. The employees just needed to move this barrier into place, and it would be an automatic 5 decibel reduction in their noise exposure. One of the things that we suggested was they could have a little bit larger barrier that extends a little bit further toward the bottom end. But yeah, they have the right concept, but they didn't always use it. This is a company. This is a company that made little. They made labels, and they would make paper tape that you might see on an old cash register. We don't see a lot of those anymore, but they would make small rolls of paper. So this part of the process was a baler, and all that was happening here was extra paper that wasn't used. They would recycle it and recycle it into bales of paper for eventual recycling of that paper. So when we went into this company, one of the things we saw was they had a barrier wall here. I've mentioned barrier walls. So just looking at that barrier wall, one of the first things that comes to mind when I look at that is I'm probably going to suggest that barrier wall be a little bit taller, maybe a little bit wider, but great idea. So this is where the importance of taking octave band measurements comes into play. So when I looked at my octave band measurements for this area, and this is just looking at that baler, just a closer look at the motors that run that baler, and you can see little scraps of paper all over this. In addition, I'll step out of the noise arena. One of the concerns we also had here was a fire hazard risk because they had all this paper and dust near these motors that generate heat. So we recommended that they deal with that, they clean that up. But so looking at the octave band measurements for this work area, one of the things that we saw was we had quite a bit of low frequency noise. We had some peaks right around 400 hertz, and then going into the mid frequencies also. So that was, I mentioned earlier, a barrier isn't great for low frequency noise. So one of the things that we're going to look at for that type of operation is to use vibration isolation, and I'll get into how we might do that. So that's an example where, yeah, initially looking at that's a good noise control. But looking at the octave band measurements, I might come to the conclusion that they need more. They need more than just a barrier. The barrier is going to help with some of those higher frequency noises that are generated, particularly in the nearby areas. But we also want to reduce some of that low frequency noise with vibration isolation. Just a couple of examples of a barrier that are in disrepair or not quite effective enough. This is also a foundry operation. They have vinyl strips here. The vinyl strips will work somewhat, but they're not thick enough and they're not long enough. So again, the company has the right idea. They're in the right direction. They're doing some things right, but they just need to take a few additional steps to improve this. And this is the same company, a different part of the operation, where they put up these quilted curtains to reduce some of the noise. Their parts will come down this conveyor and then move into another part of the process. And this is in complete disrepair. So that's just simple maintenance. So they have the right idea, but their execution is poor and their maintenance is poor. Here's an example of noise control for impact. So if we're taking a hammer, hitting the end of a chisel, we're going to get a lot of impact noise as the hammer strikes the end of that chisel. So there are tools that are available to reduce some of that. This is just an alternate type of tool that has a polymer head on it. And so when the hammer strikes a polymer head, that force of impact or that point of impact is going to generate a little bit less noise. And then this polymer here is going to reduce some of the noise that you get, this ringing noise that you get when you strike the chisel with a hammer. So a combination of a couple things. It's just an alternate tool that's available. So if you had a workplace that was doing a lot of chiseling and using hammers on chisels, switching everyone to this type, an alternate type of tool, might be helpful in reducing the noise exposures. Here's an example of noise from falling objects. Here's let's say this is metal, something falling into a hopper. We're striking the sides of the hopper. And this is an example of a noise control where all I'm doing is modifying where I have this hopper placed. So instead of the pieces falling down here, we have a pretty large free fall height. we're just reducing how far these pieces fall. That alone might reduce the noise exposure, might reduce the noise generated by this process. This costs nothing to do this type of thing. All we're doing is replacing this, moving it from one place to another. We're just moving it a few meters. We'll reduce that free fall height. This facility had a lot of these metal bins, so we could increase the thickness of these bins, increase the dampness of it, so if something strikes a side, it's not going to generate as much noise. These bins could be replaced with a durable plastic composite material. Again, the purpose of that would be to generate less impact noise as the piece of equipment, as the casting falls and drops down into this bin. This is a NIOSH study. I wasn't involved with this. These are colleagues of mine from our mining research group in Pittsburgh, Pennsylvania in the U.S. So this is a continuous mining machine, and reduction in noise exposure, the workers in these areas. So that's a substantial improvement. It didn't cost a lot of money. Once the manufacturer reformulated the whole process, it really didn't increase the cost of this equipment very much. But it did take some effort. So that is something that's now available for mining companies to use, are these machines with the polyurethane flight bars. When we have pieces of sheet metal or surfaces that vibrate, there are a couple different ways to reduce that vibration. There's what we call free layer damping, unconstrained layer damping, and constrained layer damping. Free layer is just simply applying a mastic material to the surface to reduce the ringing of that surface. Unconstrained layer damping is we have a base layer, it might be a sheet. It might be a sheet metal, and then you have a damping material that's part of that, and that is applied to that vibrating surface. And constrained layer damping is just simple, or is similar. It's just a sandwich of material. So you have two constraining, or you have a constraining layer between two base layers, if you will. You have your damping material. So all of these things are intended to do is reduce some of the vibration from a flat metal surface. I mentioned earlier that we have an ongoing project with a company that's cutting metal. This is a foundry. They're cutting. This is a worker cutting excess metal off of a casting. We get a lot of noise from the saw blades. As this saw blade contacts the metal, you get a ringing of the saw blade. You get noise from the contact of the teeth on the piece of metal itself. So a couple of things that we look at for reducing noise exposure, or reducing noise as part of this operation. One are using composite saw blades instead of metal, using blades that are designed to generate less noise. So manufacturers have blades that are designed to generate less noise. Things like making sure the teeth are always sharp. Sometimes adding a damping collar onto the blade. Also, it's not reflected on the slide here, maybe reducing the rotational speed of that saw blade also might be an effective control measure. Typically, it might require a combination of all of those things. This type of noise is quite difficult to control, and yeah, that's what we're faced with this ongoing evaluation that we'll be doing. Is company has installed some of these. Companies installed this damping collar, but they're still seeing high noise levels. So we'll be working with them and try to figure out what might be some alternate approaches they can use. So I mentioned vibration isolation. What we're talking about here is as we have a piece of equipment that's vibrating, what's occurring is that equipment is vibrating the surrounding surfaces, and that itself generates noise. So what we want to do with vibration isolation is we want to keep that vibration limited to the machine itself and keep that from being transmitted to surrounding surfaces, which that will reduce noise levels overall in the workplace. And there are lots of different materials for vibration isolation: rubber, felt materials, cork materials, springs, and each type of material has a different purpose, has a different durability. So when someone encounters this, it does take a bit of work to identify what's going to be the best material. And part of that's going to depend on how much vibration is generated and how much and therefore how much vibration needs to be controlled. This is this is our canning company again. This is one of the initial stages of the process where they're taking sheet metal, punching circular holes that will eventually be little circles out of the sheet metal that will eventually be the cans. But we've got a large stamping press that was mounted directly to the concrete. And looking at the octoband analysis, we're seeing quite a bit of low frequency noise, and that's a reflection that we're getting that vibration transmitted from the equipment to the surrounding surfaces. So that leads us to the conclusion that one of the things we need to do is look at vibration isolation. Just another example, similar, where we have a piece of equipment that's mounted directly to a concrete floor, and then another piece of equipment that is actually using vibration isolation springs. This was somewhat interesting in that this particular piece of this company, when we looked at the octoband analysis, they still had very high frequencies, only at 8 hertz. So it was very high frequencies, still at 8 hertz. So one of the suggestions we had for them, it might be putting different types of springs on this piece of equipment. Here's our grinder. We saw a picture of this work area or this operation earlier. It's a better picture of our 30-inch grinder. So we're getting a couple different noise sources here. This worker is using the large grinder and then also using a handheld grinder. So looking at the octoband measurements in this work area, we're seeing high levels in higher frequencies. That's primarily going to be from the handheld grinder as it's contacting this piece that he's grinding on. But we're also seeing some low frequency noise, and that's really from this piece of equipment. A lot of times they would leave this running while they were doing this job. So that was one of the things that we recommended was turn off this piece of equipment when you're not using it. Reduce some of that vibration that's generated by the rotation of this wheel. As this wheel rotates, that alone generates some vibration, and then you get additional vibration as this person is doing grinding on the large grinder. A couple other things that they could look at is reducing the vibration or reducing the rotational speed of the grinding wheel. Maybe a different type of grinding wheel might be able to do the job, but generate less noise. One of the things that we recommended for this part of the operation or this aspect of it is this guy was doing work. We have some plywood here, but he's also doing work on a metal conveyor. This is just a roller conveyor. So one of the things we recommended was when they were using that handheld grinder to place that piece of metal onto a vibration isolation mat to reduce some of the noise as he's doing grinding on it. Reduce some of the noise generated just by that process. This is our canning factory again. These are machines that place. They're called a Necker machine. They put a flange on the top of a can that eventually, once the can is filled with let's say soda, it'll allow the lid to attach to the top of the can. So these motors move at high rotational speeds and generate quite a bit of high frequency noise in the work area. But because of that high rotational speed, it's also generating a lot of low frequency noise. So we've got a combination of noise occurring. So that's going to take a combination of control efforts. One is vibration isolation, most likely, for this, and then perhaps a noise enclosure or a barrier between this piece of machinery and the walkway. So workers would walk in this walkway, and they probably had about 30 of these, would walk in this walkway between rows of these Necker machines, Necker and flanger machines. So that might help reduce that worker's exposure. In another part of the operation, they also had a motor and blower on a metal platform. So again, that could be something that could be enclosed, perhaps, to reduce some of the noise levels in that area. We would see, when we would walk underneath this piece of equipment, we could see an increase of noise exposure just walking underneath it as we walk through that area. Looking at pneumatic and compressed air noise, this noise is really movement of air. So movement of air, movement of high-speed air with compressed air nozzles or guns generates quite a bit of noise. Compressed air noise in some workplaces can be 1/4 to 1/3 of the noise problems might be related to that type of noise. And that's really caused by turbulence as air is exhausting out of a tip at high speed and interacting with the air that's not moving around it. We get a lot of turbulence, and as a result, you get a lot of noise generated. It is, fortunately, an easy noise to control in the noise control community in relative terms. And also, if we can reduce compressed air usage, companies can save quite a bit of money. So this is just an example of the relationship between air pressure and noise level. So at this particular frequency, at around 6,000 hertz, at 55 pounds per square inch pounds per gauge pressure, we've got 122 decibels noise. If we reduce the air pressure in the system to 30 pounds per square inch gauge pressure, 111 decibels, and down to 103 if we reduce the air pressure down to 20. So if you can have a reduction in air pressure and still do the job, you could generate, this is almost 20 decibel reduction in noise just by reducing the air pressure alone. And that also will save, will use less, the company would use less air pressure. For air guns or nozzles, there are solutions that are available that are actually nozzles designed to generate less noise as air is exhausting that tip. And these can generate more than 10 or more decibels of less noise just by having a different nozzle. It's a relatively inexpensive fix and can be quite effective in reducing noise. This is another picture from the drug manufacturer that we saw the enclosure from earlier. So as part of the process, they had a system with solenoid valves inside. Air would exhaust out of these ports and generate a hissing noise. We get the ports were threaded, and so a lot of air turbulence is generated, a lot of noise generated. So installing something like these diffusion type mufflers, that alone is that's going to reduce noise levels up to 10 decibels, maybe more, just depends on the process. Just another example, anytime we're exhausting out of an open tip, if we can replace that open tip with a nozzle designed to generate less noise, we may have substantial noise reduction and also potentially substantial less use of compressed air. In this example, this is from a manufacturer, but the example they're providing is that they're getting 14 to 18 decibels noise reduction and 23% to 30% less air consumption by replacing these open tube design with a compressed air nozzle designed to generate less noise. This is the company I highlighted earlier that made the small rolls of paper. So this is just part of the operation. They had a leak in their compressed air line. This is a compressed air line, some hose or tubing for compressed air. They had a leak right there. And when I pointed that out, one of the maintenance personnel, they put a piece of duct tape over here as a temporary fix, and that alone reduced the noise level 10 decibels in that work area, putting a piece of duct tape there. So eventually they were going to follow up and just replace this section of hose. But that's a maintenance issue. That's an issue of just doing a simple fix can have a substantial reduction in noise. This is just another example of poor maintenance. This is a foundry, and right here, what we have right here, this is just a little piece of metal that they use as a diverter. So as parts were coming through this process, employees would either send the parts down this way or send them over here. And so they were just diverting parts. But this thing rattled because it wasn't tight. It didn't fit tight into the process, into the system. So when it was rattling, this was our noise frequency spectrum. We're getting high-frequency noise here. When they just tighten this down with some bolts, with some clamps, we reduce the noise level about 7 decibels. Again, there's no cost for that type of fix, but we're seeing a substantial reduction of noise from that fix. I mentioned work practices. This is an example. This person right here would take parts, scrap parts, and would toss them into this bin right here. Now, I talked about bins earlier, being when parts strike a metal bin, they bang the sides of that bin, generate a lot of noise as that's happening. So a couple things that can occur here is, one, let's move this bin closer to where this employee is standing so he doesn't have to toss parts quite as far. Another example might be just modifying work practices. So instead of throwing the parts in the bin, the worker is more gently dropping them into the bin. And then the examples, what I had mentioned earlier with having thicker walled bins, thicker metal walls on there, or using a durable plastic polymer might also reduce the noise. Here's an example of, instead of hammering something, we can use we can use pliers to bend it in shape. This generates a lot of noise. This generates almost no noise. All right, let's see if this works. All right, maybe. Let's see. All right. That's not working. That's a video clip, but the video clip isn't working. So this is what I would call just-in-time PowerPointing. This is a video or a picture that I took last night at, I don't know if anyone here was at the party last night downstairs, but I used a little sound level meter app that I have on my phone, and Dr. Kerwin and I took a measurement. He took a video of me holding the phone there. So what about this kind of noise here, where we're about 94 to... Oh, all right. It is working. Well, upside down. All right. Well, I'm not sure why I wasn't upside down when I took that. But so what about that kind of noise? How do we control that kind of noise? Well, it's pretty obvious. We can turn down the band. We can turn down the volume on the band system. But at 95 decibels or at 97 decibels, if we're exposed about 30 minutes, we would be over an 8-hour time-weighted average exposure limit. We've actually had some health hazard evaluation requests related to noise from music venues. And folks in Australia have done quite a bit of research in this. but we've had one from a number of years ago from a casino. A worker in a casino was concerned about noise in the area where he worked. We didn't actually end up doing an evaluation at that workplace. But that was one of the things that they could do is they could reduce the sound level, they could reduce the level at the soundboard, but a lot of times there's a lot of resistance to that. So it is something that we encounter. All right. One of the things that NIOSH looks at is a buy quiet process, where what we want to do is encourage folks to work with the equipment suppliers to ask for and provide equipment or equipment that generates less noise. So briefly, I'm running short on time. I'm going to talk a little bit about hearing protection. Lots of different types of protection are available. So under any circumstance, there really should be a hearing protection that would be suitable and adequate for someone to reduce their noise exposure at the ear. And remember, we always want hearing protection is kind of our last step. We want to try to control the noise other ways, and when that doesn't work or that's not effective, then we want to go to hearing protection. And we have lots of problems with people wearing it wrong or not wearing it at all. And really, one of the biggest barriers to hearing protection use is comfort. If it's not comfortable, people generally aren't going to use it, or they're not going to use it correctly. So that, by far, is one of the biggest barriers. Secondarily, we hear from a lot of workers that will tell us, well, if I'm wearing hearing protection, I can't hear the equipment, or I can't hear my coworkers. And there are ways around that with selecting the proper type of hearing protection, communication earmuffs. So there are some ways to work around that. Sometimes there's a learning period for people to get used to hearing their workplace, hearing the sounds in their workplace while they're wearing hearing protection. I want to mention that when you have hearing protection, on the package there's a noise reduction rating. And this is really based on measurements that are done under a controlled laboratory setting. But in the real world, people don't wear hearing protection perfectly. So what we do when we're trying to estimate how much attenuation a hearing protector is actually getting, we apply this formula to the hearing protector. So all I'm doing is taking the noise reduction rating that is on the package, subtracting 7 from that, dividing that by 2, and that's going to give me how much attenuation that hearing protector is providing. And that will be an indication of how much noise exposure a person might have at the ear when they're using that hearing protection. And this is really to address the problem of imperfect fit. Usually hearing protection doesn't fit perfectly. One of the things I do want to point out, when noise levels are over 100 decibels, we recommend that people wear dual hearing protection, both earplugs and ear muffs. For inserting hearing protection, especially the foam, if I'm talking about the foam insert protection, we're looking at making sure workers roll that into a small cylinder, insert it deeply into the ear canal, and that's going to provide the best fit. So there are systems these days that you can actually do fit testing, like you would do respirator testing, fit testing. You can do the same thing with hearing protectors. To provide an actual estimate of a worker's actual fit. How much attenuation are they actually getting from the earplug they use? And why do we want to do that? This is research that a researcher at 3M, Elliot Berger, did a number of years ago, looking at how much attenuation different types of hearing protection was actually providing when he looked at a whole array of different types of hearing protectors, comparing the NRR that's on the package to what the attenuation he was actually getting, and we see a substantial difference to those. Just another example, this was a company that used hearing protector fit testing. Before they used fit testing and did training on employees, they were getting very little attenuation or very low attenuation of the hearing protectors. After they did fit testing and did training for the employees, they found that employees were having much better attenuation of their hearing protectors. Like I said, there are lots of different types that are available. I'm not going to go into the different types. They all have pluses and minuses. They all have benefits. They all have some downsides. And lastly, I just want to point out that there are chemicals that people can be exposed to in the workplace that we consider autotoxic. So what that means is, in some cases, these chemicals, without any noise exposure, can affect hearing. So even if a worker is not exposed to noise, these chemicals can have an effect on the hearing mechanism and on hearing. And then if we're in a situation where we have noise exposure and exposure to these chemicals, in that type of situation, it may exacerbate the problem. It may complicate the problem of combination of noise exposure and exposure to these autotoxic chemicals. All right. That is the Cincinnati skyline. I want to thank you for your attention, and I think we have a few moments for questions if folks have questions. And that is my contact information. And for all of us at NIOSH, if you have questions that you have about anything really related to occupational safety and health, we're glad to respond to those questions and try to provide an answer for you. Fortunately, I work in an environment where I work with highly educated people, and if I don't know the answer to something, I know I have a colleague that probably does. So do we have questions? Yes. Slow response is just slow response is a setting for sound level meter and dosimeter that was specified as part of ANSI standards, American National Standards Institute, that we have to use. So it was something that was established years ago, and that's why we do it. It's an artifact of something that's established and required to be done. We would have probably very little effect using fast response versus slow response. It's not going to make that big of a difference in the overall sound level that we would measure. Yes. Do you? Okay. Interesting. Yeah, I wasn't aware of that. Now you may have, where you might have a difference if you had a lot of fluctuating noise levels, there's where you might see a little bit more of a difference. You're going to see less of a difference if it's continuous. But it's really just an artifact of equipment. When equipment was initially, when dosimeters initially came out, how we would read a dosimeter, or I should say sound level meter, was a little needle. And so slow response, just if you're using fast response, that needle would be flapping like this. So slow response just diminishes that. So it's it's an artifact of that. At some point maybe it'll change, but for us, not in the near future. Yes. Oh, I'm sorry, yes. So the question is, where does the noise reduction rating come from? The formula of NRR minus 7 divided by 2. That's something that two sources have that. That's something that OSHA uses in some of their, that's what compliance officers use when they're estimating how much protection a worker is having with their earplugs. And that's also in the NIOSH criteria document, where we have that formula in the NIOSH criteria document as well. So that the question is that formula based on research? I would say it's less based on research and more based on a general guideline to take into account that we just have such poor fit of hearing protectors. So it's a conservative estimate of how much protection a hearing protector is providing, but it's really not that I'm aware of, based on a lot of research, to come up with that specific formula. All right, well, thank you for your attention. Have a good evening.